Welcome to the Silego Technology CMIC and IoT Webinar. We're going to go ahead and get started right away, but first, just a little bit on the agenda. The first part of the presentation, we're going to cover just IoT, what's new, what are some of the problems, and what is the IoT revolution all about. And then from there, we'll immediately pop into how does Silego play in this particular area. How do we make IoT devices better, cheaper, lower power, etc.? And then we'll discuss some of the advanced techniques that make IoT and our CMIC chips work so well together. So the first thing, let's talk about IoT. First of all, I like to say IoT is not really new. It's a rebranding of a classical problem of you've got to sense things, you've got to process things, and then you got to do something with that process data, like a warning. You think about a guy in an old crow's nest. He's looking out looking for the icebergs. He's got his optical sensor, his rod and cone sensor in his eyeball. He's looking through a magnifying glass. He's got a sophisticated 70 dB signal to noise ratio voice alarm. What are some of his problems? Well, he's got to eat, so he's got a battery life problem. He's got over temperature performance problems. Who wants to be up there in, minus 40 degrees C weather? And then, of course, he's a person, and so just like a microcontroller, occasionally he has reset issues. Think about a town watchman in Switzerland or something like that, walking around with a spear. He's an armed drone with a mobile wireless optical sensor with active illumination and a bell alarm. What are his problems? He's got battery life problems. He's got over temperature performance problems. He's got synchronization issues. Like, he's got to make sure he doesn't go the exact same place the other watchmen go. He's also susceptible to shock and vibe if he gets clunked over the head. These are all IoT problems, and we deal with them today just like they dealt with them then. Even wireless communications isn't new. The only thing that's really changed is how many bits per second. Instead of going at 0.1 bits per second, we're up in the gigabits per second. You think of the old Chinese wall and their optical wireless communication from one watchtower to the next tower. My heritage as being part Haida. Some of these guys did smoke signals and were able to communicate over vast distances some very primitive information about where they were and what was happening and where the buffalo roamed. So what is changing? So we know the problems and the things we need to address aren't really changing, but what is changing is our ability to address these problems. So we've come out with technologies that are a lot cheaper, power consumptions that are lower, better materials. The yields are, continuously improved to drive our costs down. This cost being driven down has allowed us to measure more things, take more data. The performance has been greatly improved. Our data rates going from 0.1 to the gigahertz. Our accuracy is improved. Our over temperature performance is improved. The system size, what it takes to do things, is dramatically shrunk. The reliability is dramatically improved, improving with higher quality. Now we can afford redundancy. We can afford a lot of security. There wasn't a lot of security when you were doing smoke signals. Virtually everybody could see what your data had to say. Nowadays, we can provide AES, 128, 256, these kinds of encryption modes. So Silego is part and parcel of this revolution. We're helping IoT changes happen faster, at lower power. We're doing it in smaller physical dimensions, and we're doing it at higher quality. Now, when we look at what is the IoT revolution in reality today, why do people feel like we have a revolution going on? The reason why is because recently there's been dramatic advancements in battery technology, particularly lithium ions. We're now allowed to ship products with energy densities that we never could achieve before lithium ion came on the scene. This has allowed us to have a lot more power by which to do a lot more interesting things in terms of sensing, a lot faster communication, and not wind up with massive sized products. The next thing that's been happening is Moore's Law. Moore's law is basically, in the semiconductor world, talks about a doubling in circuit complexity every 18 months or so, which has dramatically shrunk the cost of transistors and the size of transistors, allowing us to do enormously complex things in tiny, tiny little areas at costs that are just mind-blowing. The cost of an individual transistor is so low as to be almost to be non-consequential in modern products. This has taken an old cost curve and made a new cost curve. And so we are able to go gather data in areas where we would never have taken data before because it was too expensive, but now we can. I like to think about this as almost like a gold mine where the easy pickings has already been done. But if you can come up with a new way to go mine that gold, you can enter a lot more new ground and be able to derive a lot more value out of the earth than you had before. The same is true in the IoT revolution. Before, we wouldn't have done a fitness band because it just would have been too expensive and the band would have been too large. But with all of these advancements, now we can take a lot of medical data, slap it right on your wrist. I, for example, had an arrhythmia problem and still do occasionally. Before, whenever I would have this, occasionally I'd have to show up at the doctor's office or I'd show up at the ER if it was bad enough, and they would slap it on, and inevitably I'd arrive into the parking lot, and that would cure my arrhythmia. And so when they'd hook me up with the machines, they wouldn't be able to see the arrhythmia. And you know, then you go home, and what an expensive non-event that was. Well, with today's modern IoTs, they can actually put all that sensor, put a battery on it, tape it to your chest, and you can live with it for 2 weeks. And so your heart can be tested solidly for 2 weeks, looking for those rare events when the arrhythmia would occur. Once those arrhythmia occurs, then the doctor can actually read those waveforms and determine what's going on with your heart in that condition and not have to wait for it to show up in a very, very expensive ER or a very expensive hospital room. And so sleep studies and all these kinds of things are being done now with IoT devices because we have a new cost structure, because we have a new size structure and smaller batteries and this kind of thing. Now, cost is also very instrumental here to some of the points that I'm going to make later on in the presentation, because power consumption cuts two different ways. I use two different examples in this slide. One example is an alkaline battery, which is a non-rechargeable battery in this particular case, and lithium ion, which is rechargeable. Now, when we look at the battery cost, it is a very substantial part of the cost of an IoT device, a mobile IoT device. So when we talk about lower power consumption, we don't just mean increasing the life of a product. Very often, IoT designers want to lower their power so they can shrink their battery size, so they can shrink their product size, and they can shrink their cost. It isn't always just, you know, trying to get out and have a 10-year life of a product, which obviously is another good thing. The same is even more true with lithium ion. Lithium ions are more expensive, but of course they have the added benefit of being rechargeable. But anything you can do to cut the power there can also cut the cost and size of the lithium ion battery. So this is a large focus in terms of why IoT wants to be lower power. A lot of it is because so much of it is driven by cost. Another point that I'll like to make is IoT has always been around at the expensive nodes. For example, you know, if you want to track a cargo container, that capability has been around for many, many, many years, and people don't mind paying a couple $100s for a node, you know, to track a $20,000 box or a $100,000 box. But really what we're talking about today when we talk about the IoT revolution is a radically lowering of the cost structure so that we can just start tracking all kinds of things that we never would have tracked before because it wouldn't have been profitable. But with the lower cost, we can do that. So let's look at a basic low-cost reference block of an IoT node. You've got a sensor, you've got a little bit of timing, you've got some RF, you need a little bit of security, you've got a battery, usually lithium ion, a processor of some sort, and some data logging memory. It's pretty much your most basic IoT node. Now, That's not really where Silego would play. Silego plays when you start thinking, I want to differentiate my product other than in software or firmware. I want to actually do something new or novel. So you take your Qualcomm reference design and you go, okay, I want to add a new sensor to it because I have some new capability I want to offer the world that's going to allow my product to sell better than your competitor. So you drop in a new sensor. When you drop in that new sensor, there's no power to support it, so you need an LDO. Your processor works at 1.2 volts. Your new sensor works at 2.8 volts. How do you communicate with that sensor? You need level shift circuitry in order to do that. Then you go, I want a better display than the one that this reference design offer. I want something that's a color display. That color display has its own power sequencing. It has its own timing that it takes from the time the power is first applied till the time it's good. So it needs to have a better reset or a different reset. You want to use an embedded battery, maybe than a battery that can be unplugged, and the customer doesn't have the benefit of just yanking the battery out and plugging it back in to do a hard reset. Therefore, you need a more robust reset. Then let's talk about even more features. Let's say you want to add a few more buttons to do some manual entry, maybe a touch button. You've got to debounce that. Maybe you want to do some let the user know when that embedded battery is wearing out, and so you want another comparator in there. Maybe you want some vibration capabilities, so you add a haptic buzzer. Maybe you want to have a RGB LED to indicate some other kinds of, maybe that your Bluetooth is linked, or whatever your heart's content is to make your design. And next thing you know, your little tiny reference design is now grown in size by 3 or 4x. You have all this circuitry placed all over your IoT device, and it's neither low power, it's not cheap, and you're wondering how you can be cost competitive in the market, and how you can be small as your competition. And the answer is low-cost configurable mixed-signal ICs from Silego. That is the answer to this problem, and we ship hundreds and hundreds of millions of our chips to companies that find this as an answer to this particular problem. So I'll show you really quickly using that last slide how the PAK chip can sort of clean up your design. You'll notice that on your sensor we now have PAKs with LDOs, so you can provide power to that new sensor, you can provide level shift capability over to it. All that's cleaned up in a PAK. That embedded battery can be checked out with one of our comparators. Those buttons can provide the touch sense, it can provide the debounce, it can provide the display driver communication and reset, it can provide an LDO for that display driver, it can provide output buffers that are strong enough to drive an RGB, it can provide the I2C necessary to give you any kind of color on that RGB, it can provide the drive circuit for that haptic circuit. And you can suck all of this up into one custom chip that can be designed very, very rapidly at a very low cost. So what do our GreenPAK chips contain? What do these Silego CMICs, these configurable mixed-signal IC, contain? They contain state machines, ADD converters, logic, clock, watchdog timers, comparators, level translators, MOSFETs, all of these types of devices. And they make it in such a configurable way that you can integrate all of those types of circuits that I was showing you before in one little tiny circuit that can go on your board, sometimes two, depending on what you're trying to do. And this can clean up your design and make it look as if it was a reference design from the word go. I mean, really tight, really compact, not all that wasted, another word I call it is circuit trash. And it can happen very, very rapidly. So what is the value equation of Silego? We have 3 unique capabilities for our CMICs. One, we have advanced circuit design. We put on non-volatile memory, which allows configuration and the connection of all of those circuits that you would normally use. And we have a comprehensive set of software tools that allow you to very, very rapidly make the particular chip that you want. So as you're sitting at your desk with our tools, our hardware, our software, you basically are an IC designer. So instead of complaining about not being able to find exactly the right, chip on DigiKey, or the exact right reset or power sequencer or the exact right RGB driver, you can just build your own. And typically in just a matter of hours if you're experienced, or a couple of days if you're inexperienced, you can knock out your own particular chip that's perfectly suited to your application, saving massive board area and actually saving a ton of cost. A lot of people, when they hear the word programmability and NVM, they immediately, their minds go to, oh, I'm talking about something that's at the cheapest 50 cents and $1 in many cases, sometimes $2. That's not the case with our particular products. I wanted to give you a real life example here of our little tiny programmable chip, our 1 by 1.2 millimeter programmable IC. This is almost like pepper speck small. It's really hard to believe that in 1 by 1.2 millimeters, you can get an NVM programmable logic IC that sells well under 15 cents. Now, I wanted to compare that with real stuff on DigiKey right now. So if you go up on DigiKey right now and you look at the cheapest logic gate possible, like an AND gate, and you search on that, you'll find that costs 2.1 cents. We put 10 of them in this little 1 by 1.2. Now, you will look at it, the size of one of those logic gates that costs 2.1 cents, it's larger than our chip. Even just one of those AND gates is bigger than our entire chip. But there you can have 10 of them. You can also see that we include a supervisory circuit on this. The cheapest DigiKey supervisory circuit. We don't care how it performs. I just picked the absolute cheapest one, 7.9 cents. Then I assume that there's about 3 cents of related timing circuits. So that is equivalent to 32 cents of discrete value. If you actually bought the chips on DigiKey that equated to what we put in there, you would pay 32 cents. And this I used at their highest volume that they did. In some cases was 150,000 units, 100,000 units. The cheapest MCU on DigiKey is 28 cents. So in this case, if you use the entire capability of the chip, it probably would pay you to go to an MCU at 28.8 cents, even though the discrete value is 32 cents. This means that a GPAK is easily 50% less cost, more than 90% footprint savings against either the discrete value or the MCU, plus it's your own IC, so people can't copy what you're doing, and it's your own part number, and you have the security of going to market with your own design closed up in this particular IC while saving a ton of money. I hope that point is real clear. And you got to remember, this is our worst case value example. Now, let's take the next step up and let's do the same exact thing. The next step up is our 1.6 by 1.6 millimeter programmable IC. And in this case, we've added a couple of ACMPs, analog comparators, and we've added a voltage reference. Now, if you start to compute the discrete cost value of this, you come up with very high numbers. I mean, you're starting to now talk in terms of 50 to 55 cents worth of value in the discrete world. So we're just ignore that and say, okay, what would people rationally do? Well, the cheapest microcontroller that's got a couple of comparators on DigiKey is 33.3 cents. And so our GPAK 10, once again, is more than 50% cheaper than this, more than a 90% footprint savings against that particular device. It also offers you power savings. It offers you a much faster design process, plus it's your own IC, plus it's your own part number, and it gives you a whole bunch of different advantages that GreenPAK gives you. Now, that doesn't mean that you can go without an MCU in some cases, don't get me wrong. MCUs are beautiful for data processing. That's not what PAK chips do. What we're talking about are these control applications where you're sensing the battery, you're checking out, you're taking button inputs, you're driving a motor, you're driving an LED, that type of thing, not taking lots and lots of data that's coming off an accelerometer, filtering it, trying to determine where a shake or vibra occurred, and doing some XY analysis or anything like that. That's all data processing. MCUs are much better for that job. That's not what we're doing. We're talking about control. Now, so as we look at a real life example of what I've just said, that went to a customer, and there's a reason I kind of leave this small so you can't tell what customer it is. But this real life customer used 55.8 square millimeters of their board, and when they had everything integrated, it was 6.5 square millimeters. They saved 14 components in this case. These are very typical examples of these types of control circuits getting integrated into a particular GPAK or CMIC. I could also show you examples where up to 30 or 40 components were also integrated, and we even have comments from some of the world's top tier consumer marketing, product companies saying that they basically couldn't have done their product if PAK didn't exist as a solution, and they certainly couldn't have done it in the time frame they did. They would have had to gone to a pure ASIC solution where they paid a large NRE and had a custom chip made for them, as opposed to just pulling an off-the-shelf programmable part, configuring that with our schematic capture software, and having and being able to get to market very quickly. So, in our last seminar, we talked about what are the differences between GPAK and MCUs. So I just wanted one slide here to very quickly go over what the differences between GPAK and MCU are, just as a quick synopsis. But if you want a complete hour on the subject, go look at our library of webinars and re-listen to that one. But really quickly, first of all, no MCUs, programmable MCUs, sell for between 10 cents and 33 cents, as I already showed. GPAKs are fundamentally lower power than MCUs because they're event-driven architectures. They are not clock-driven architectures. GPAKs respond over 100 times faster to interrupt events than MCUs. So if you need critical timing on an interrupt event and you want that to happen so fast that you don't even think about it, GPAKs are a beautiful way of simplifying your ISR routines. Next, think easier firmware and less power consumption. Every time you get an interrupt that comes into a microcontroller, you got to think, how is this going to play with the rest of my software? I got to make sure I don't crash anything while I'm handling the interrupt. I've got to make sure that I put monkey around with my clock speeds, make my clock speeds go faster, make sure that my memory stacks are all happy and nothing will crash. Obviously, that's possible, and engineers who do a great job at that are very valuable. However, in the GPAK world, you don't have this problem. We don't have memory stacks. We handle these interrupts very nicely. We play very nicely with microcontrollers so that you don't crash your systems. These GPAKs are awesome for event-driven asynchronous inputs. It's not a problem. In fact, it's really, really easy for us to handle those things. And firmware engineers are very appreciative of when a GPAK is put down next to a microcontroller, because a lot of times their firmware gets a lot cleaner, has a lot less disconnects in it, and is a lot less susceptible to crashing and having problems. The next thing is GPAKs, since they're not built on super advanced processes, we can direct drive heavy loads at higher voltages, where many microcontrollers that are advanced are now that their power rails are down at 1.2, 1.8 volts, this kind of thing. You can't even direct drive many LEDs at those particular voltages. The next thing, because GPAKs are an asynchronous architecture, we don't need a voltage regulator. We can operate directly from a coin cell battery, a lithium-ion battery, across the entire range without the need of an additional LDO. And finally, GPAKs cost less per pin than an MCU. So rather than, if you run out of pins on, let's say you've got a 32-pin MCU in your design and you realize, wow, I don't got enough pins anymore, rather than move all the way up to a 48-pin MCU or a 80-pin MCU, think about just adding a GPAK. It's a lot cheaper way to go than generally to jump up to the next generation. Just leave the MCU where it is, use our I2C, use all the I/O that are associated with our GPAK. And in addition, then you get all the unique capability that comes along with an event-driven architecture as opposed to a clock architecture. So you get the best of both worlds. When you need a clock for data processing, you got it. When you want a ISR processor, so to speak, you've got that as well. You get the best of both worlds. So anyway, once again, we love MCUs. This isn't a you got to have this or you got to have that. Why not have both? Why not have both tools in your tool bag? So next, The traditional designs are one product, one development. One of the reasons why Silego is growing as fast as we are is because we've offered a new level of configurability at a new price point that's never been available before. Very few people in the world miss the point of configurability and being able to do that at the last moment. The problem has always been is configurability costs money. And configurability is provided by NVM. But what Silego's been able to do is to provide that configurability, that last minute change to our product so that we can stamp a new part number on it, have your unique circuit on it. We've been able to do that at price levels that are just absolutely unheard of. And so buying discrete supervisory circuits and discrete comparators is not really saving you money, as we proved earlier. So the other beautiful benefit of this is we actually can have millions and millions of these parts in inventory just waiting for their final configuration, and so we don't short our customers. You can imagine the inventory nightmare that is the semiconductor, the traditional semiconductor business, where you have a whole number of different processes that you've developed as a semiconductor supplier. You take something as simple as an op-amp, and you bend this 4 different ways on one particular part number. You have hundreds of different op-amps, you have hundreds of different temperature ranges, and trying to keep all that in inventory is just a nightmare and really, really tough. That's not true when you could program and have very, very few products in inventory and then just customize how those things are brought out. We can even trim so we don't have problems with binning and all of the kinds of nonsense that is the regular part of the business. And as a result, we pass those savings along to our customers. So at Silego, we have what I call the Southwest Airlines model of the business. We ship our things in very few different package styles. We have one type of tester, one type of process, one type of flow, very few bins, and as a result, we're able to deliver circuits at an unheard of cost structure, and that cost structure is passed along and allows us to favorably compete with even low-cost discrete products. Now, not only is our devices low cost, they are also very, very fast to market. So we kind of alluded to this point earlier. I wanted to ask somebody, can somebody post if the audio is coming through again? Because I'm getting a warning here that there might be some intermittent behavior.
I think the internet connection is shaky.
Yeah, I'm not sure.
Jim says he's hearing it fine.
Okay, so I'll continue to go. Oh, somebody wrote more audio problems. Okay.
Are you on mute?
Yeah, I'm muted.
It doesn't look like you're muted.
I'll ask. But no, I am. I'm muted right here.
Okay.
I can mute it here as well if that helps.
Yeah. Audio's back again.
Okay. All right. All right, so everybody says we're back again. Sorry about that. We'll try to clean this up before we do our next webinar. But anyway, appreciate you guys' time. So the next really big point about our devices is when you think about doing a discrete design, and I'm gonna attack this from 2 different ways. I'm gonna attack it from the microcontroller way, and I'm gonna attack it from the discrete products design. On the discrete products, you've got to go pick all your parts. You got to put them all down on the board. You got to make sure you connect them all right, that you have all the footprints right for 10 or 15 different vendors. Even something as simple as a resistor is a pain in the butt, making sure that you get the right footprint exactly. Then you fabricate your board. You get your board back. You have somebody build your board. Then you got to go test your board. And if you did any mistakes, you blue wire it together. You try to get it. You dead bug a few things. And you reprocess your board, get it all built again, and then hopefully you've got it right. This is a long, arduous process. Now, let's talk about the microcontroller way, which I don't show here yet. I just talked about a traditional mixed signal design way. The microcontroller way is, well, for starters, you're almost always going to use the last microcontroller you use, because most of us don't want to go relearn all of the software, all of the compilers, all of the various bugs that you had to work around on that particular platform, whether the bug was in silicon, whether it was in your compiler, whether it was in your development system. You become an expert on those particular tools, and you really don't want to have to, spend 3 or 4 months to go learn vendor B's tool set and all of the problems that come along with that. So you just stick with the one you've got, and then you pretty much go through the same thing. Then you hopefully you've counted right and you get the right number of IOs. Hopefully your code doesn't grow, and you pick the right one with the right amount of SRAM and the right amount of flash, and you get all your board working. And when you've done all your emulation, you go back to your traditional design flow and you put in your few external components and your LDOs and your DC to DC converters, and away you go. And that's a little less painful than a pure discrete system. But if you really want to save money, if you have a very high volume application or you have a very intense application, then you go to custom ASIC design, in which you spend 3 or 4 months defining the product, then you got to do it, lay it out, then you got to fab it. And this can take up to a whole year and, $500,000 in NRE to knock out a particular product. So there's everything from the discrete world of 9 to 12 weeks to 9 to 12 months on a full ASIC design or microcontroller design that could be somewhere in between that. This is completely different than what we do at the PAK LAN. So in PAK, we have a very simple schematic capture tool. It's like going to a catalog distributor and picking out your parts, doing the schematic capture right on the screen. We now are launching SPICE. You can actually simulate some of the things if you're working in particular products, or you can use our hardware tool to quickly test it out. In just a matter of a day or two, you can have a complete working circuit. You pull it off and you got your chip, and then you go into your printed circuit design. Now, the next thing we're bringing out this summer is we're actually bringing out our multiple time programmable chip. Today, we're all OTPs, so Silego does the programming when you go to production. This summer, we'll have MTP versions where the customers can drop an unprogrammed part onto their board and actually program it and actually configure their boards in system to whatever product they particularly want to. So we're actually going to have both now coming this summer. So today, the approach is, you get our development kits. We give you about 50 samples of whatever particular part that we're running in there. I'm not sure if this is coming in slow. I've noticed that since I'm running off 2 computers here, sometimes when I hit the button, it takes a little bit for the screen to catch up. I apologize for that as well. But at any rate, I'm off to the next slide, which starts with designs in minutes. The step one, essentially get our development kit. They're available for sale on our website. Very, very low cost. You get 50 free samples in that. Download our software for free. Pretty soon we'll launch our SPICE version of that, but you can also do the design directly in our software. Then you can program a few parts directly with our kit programmer, and you will have your chip ready, your own custom chip ready in, like I said, if you're experienced, a matter of hours. If you're inexperienced, a matter of days. And furthermore, when you go to production, you send your code into Silego. We give you a custom data sheet, and all of your production is ready in 4 to 6 weeks. Typically, it's much faster than that. Typically, if you get in a push, we can, we have production programming capability within the United States as well. If you're here, which is just about a week. If you're in Asia, 1 to 2 weeks. Once again, we only say 4 to 6 weeks to give ourselves some padding here, but generally speaking, you can get products incredibly quickly because we have millions and millions of units in inventory. I wanted to give you a screenshot of the tools because it's a little hard to believe for people that are familiar with microcontroller tools, but when you look at our tools, they look pretty much like your ORCAD schematic capture. In fact, in many cases, designers can take their actual schematic that they designed discretely and port that directly into our software. You'll notice that our comparators look like comparators. Our logic looks like logic, and you know, you connect things just as you would any schematic capture device. And when you're all done with that, it's really distracting when the internet and what I'm seeing are coming in so different and so slow. So I apologize for that. Hopefully most of you have gotten our screenshot of our development system, and you'll be able to see all the different blocks in there and the comparators and the pins that go on your chip. And you'll see that we provide the capability to even label the internal nodes in your chip as exactly what they're doing. And then in our third generation, you're actually able to spice this so you can actually see what the signals are doing inside your chip. And then, like I said, when you're all done, you ship off the particular code to Silego. We give you a data sheet, you get your own part number, and then when your procurement team wants to order the chip, they simply order that particular part number. It eliminates a ton of confusion if you're like a lot of companies where you outsource your manufacturing to somewhere in Asia. That Asian manufacturer doesn't need to be confused about what to order. They order a particular part number, and that comes pre-programmed, so they don't need to have to monkey around with anything. It greatly simplifies the manufacturing back end as well. Okay, I flick to the next slide, and I'm going to go ahead and do the next one after that. It's just a nice statement. So before I closed out today, I wanted to make a few more comments about some advanced GPAK IoT benefits. What you've got today so far is kind of what I would call our first tier benefits. It's what most people see when they first look at PAK and they go, oh, there's a comparator. I can integrate a comparator. That's the first level. The next level is, oh, I've got a comparator and I've got additional logic. I could pulse power that comparator, and I could save additional power and do a lot of clever circuit techniques that I never thought I could do when I was using discrete parts. Or there are techniques that you wouldn't do with a microcontroller, because to turn on the microcontroller and then go do the advanced technique would burn more power than the technique would save. And then all of a sudden you realize you've got this little PAK chip that you can do these things. That's kind of what I would call the second tier designer, the more advanced designer. And now we're going to talk about some other issues you wouldn't classically think about as kind of what a third level designer. Starting with our fifth generation products, we included a asynchronous state machine, and it's an 8-state asynchronous state machine. Coming this summer, we're going to introduce our 6th generation GPAK, which is a 12-state asynchronous state machine. And there's a lot of benefits you get from these asynchronous state machines you wouldn't classically think about at first blush. One is they're way, way, way more secure than a microcontroller. Way more secure than ARM cores in terms of data security. First of all, people aren't familiar with them. Second of all, there's no clock. Third of all, there's nothing you can, listen to by looking at the power rails and try to figure out what's happening inside the chip. There's no continuous kinds of thing. There's no way to power spike them and to read out code out of them. None of these kinds of things happen that you would normally associate with microcontrollers that haven't been specifically designed to be secure, ultra secure. The next thing is they don't crash. There's no running code, so to speak. Everything is hardwired. So there's no classical crash mechanism. There's no infinite loops, for example. There's no memory, SRAM memories that can overflow if you put too much into them and you lose track of where you are, or junk commands or memory pointers that have lost track of where they are. This type of thing. So while I wouldn't say that, if you're really clever, you can't make a bad design that doesn't work, the point is they don't crash in classical ways that a microcontroller would crash. The next thing is they have zero static power. If you're not using the analog part of this, the only thing burning power is the power on reset circuit. And in our 6th generation pack, that's like 50 nanoamps. So I really shouldn't say zero. I should say like 50 nanoamps of static power, but it's incredibly low. The next thing is there's zero coding. It really is a schematic capture-based way of doing things. It is not learning C++, it's not learning some oddball language, it's not learning assembly or anything like that. There's no underlying micro in this. It really is very, very simple. The next thing is, somebody's asking a question, if these presentation slides will be available online later, and the answer is yes, it will be. Our Marcom department will handle that. The next thing is it has very low EMI. When you're clocking something like a microcontroller, all of the switches, all of the CMOS switches within that design, all of them are flipping generally at the same moment in time, which puts out a large EMI spike. In order to mitigate that, sometimes we make the output buffers skewed a little bit. We can use other spread spectrum techniques, et cetera, to try to get out of those issues, and those are all viable ways to do it. But our asynchronous state machine, being an event-driven controller and not having any fixed timing, is inherently low EMI, meaning you could do the same thing over and over and over again, and it will just naturally separate itself. As the temperature changes, process changes, different parts of the die, all of these things happen at slightly different times, so you generally don't line up your switching moments to compile your EMI into one big spike. The next thing that is beautiful about it is, especially for mobile application, is even if your power supply is kind of bad, the battery is discharging, maybe your RF flicked on and the battery drooped a little bit, or the power supply to this chip drooped a little bit. Since the timing and setup of the logic in this chip is not determined by a clock, an event-driven architecture, an asynchronous architecture, is almost impervious to power supply variations. I'm not saying if you don't, drop it down to zero or do something crazy, you can't screw it up. Yes, you can. But it is generally really, really tough to screw up the power supply. We also make the ASM design extremely simple. We have an editor within our tool that looks just like a whiteboard, where you draw your arrows, you say, I'm in this state, I want to go to battery check state, and the decision that's going to make it go from one state to the next state is the arrow, and you simply draw it up, and then that's all immediately imported to the logical portion of the software, and you simply hook up your connections and away you go. Dirt simple, easy. So once again, we're secure. There's no program code to hack. There's a complete configuration lockout as possible. It's not crashless. There's no memory overflows, no memory addressing, no ISR conflict kind of things, zero static power, no event, no power. That's the way it works. There's no code, nearly zero latency. Typically, when an event comes in, it's processed in 50 nanoseconds. Like we talked about in our last seminar, it's common for an interrupt to come into our chip process that interrupt, do whatever it needs to do, and go back to zero power consumption faster than the event is even detected on the lowest power mode in a microcontroller. And we're already back to doing no power. We mitigate a lot of the design the issues with supply variation because we don't have traditional setup and hold times. Now, so we continue to advance with our pack chips. Later on this year, we'll bring out ones with more analog capability that connect with even more different types of sensors, that have different types of communication schemes, that work even better with various microcontrollers, but always continuing our theme of low cost, high levels of configurability, low power, and security. So in summary, our configurability allows new innovative designs to be small and cost efficient without custom ASICs. This is absolutely critical as you try to differentiate your design from other competitors of yours. When you want to add a new sensor, when you want to add a new feature, don't blow up your design with a whole bunch of circuit trash or new custom ASICs or really expensive microcontrollers. You can just drop a GPAK in there, connect to all of those things you're trying to connect to. It looks clean, it looks small, it's low cost, and it's yours, and it provides an unmatched level of design security so that people can't copy what you're doing. The next thing is, when you get advanced at working with GPAKs, you actually can save yourself power. The size savings almost comes for free. I mean, it's almost hard not to save massive amounts of area when you use this particular type of product. But the power consumption generally gets better the more experienced you get in terms of being able to do various low power techniques like pulse powering, like not using RC time constants and using one of our counters, and lots of different power savings techniques. And then finally, the GPAK configurability typically costs 50% less than discrete solutions or MCU solutions doing very similar circuits. So I want to thank all of you for joining us on this seminar. I really appreciate you being here. Sorry for all the technical nonsense that we're going through. If anybody has any questions about what we talked about today, we'd be happy to answer those. And I'll pause here and see if anybody's got any questions. All you need to do is type them into your Q&A block you have on the screen there. So one person has asked, why 12 states and not 16 states? That's a really good question. The main answer for 12 states was the complexity of the ASM. Because of the way we wire it, it increases exponentially in terms of the amount of connectivity, and therefore it equals an exponential increase in die size as you go up. And so when we did an analysis of our database of customer designs, we found that most of the state machines actually were somewhere between 5 to 8 states, was pretty classical. And then since this was our flagship product, maybe 5% of our customers used 12 states, was pretty about the top end of that. So we just wanted to make sure that in our flagship product, we incorporated pretty much every possibility that our existing customer base was using, and that went up to 12 states. In the future, we'll certainly have parts that go a lot higher than 12 states, but today, 12 states is where we at. Any more questions? I'll wait 30 more seconds, and then we'll cut out. Okay, I'm not seeing any more questions through. Thank you guys all for joining us. I really appreciate your time, and hopefully you found it valuable. I think Trang will follow up with you guys and see how you appreciate it. So be gentle. At any rate, you guys take care. Bye-bye.